Good evening, everybody. It's 7 o'clock here in sunny and chilly Melbourne, and I'd like to welcome you all along to our free short course on the Internet of Things, presented by IT Masters in conjunction or as a partner of Charles Sturt Universities. While everybody's filing in, pretend you've got elevator music going on. I'm going to leave it for about another 3 to 5 minutes while the numbers all pick up, and then we'll start and kick off in earnest. So I'd like to speak to you soon. In the meantime, feel free to chat, say good day in the chat, tell us where you're all coming from, what you're doing, be interested to see if you've got any Internet of Things projects on the go, and we're keen to say hello. So speak to you in about 5 minutes properly. Thanks. Hi, everybody. Thanks for being patient and just waiting until we got everybody coming into the room, as it were. And again, I'd like to formally welcome you to tonight's free short course, week 1 of an introduction to the Internet of Things. That's what this week is called. My name is Shane Murphy, and I'm from IT Masters, and I'll be your host and co-presenter. We've got a slightly different format this week than we normally do. Now, let's do the bit of the housekeeping first up. Feel free to chat in the chat room, of course. Tell us where you're from. I can see there's been people from all over the world already, from Malawi, from Cameroon, from Burma, from Kenya. Lots of people from Melbourne and Australia in general, as well as we'd normally expect. A few from Malaysia. So it's great to see, and I hope you're doing well and safe and in a good place at the moment, wherever you're from, Iraq and the Solomons, all over the place. If you've got specific questions that you'd like us to answer, put those in the Q&A section. Our amazing moderator, Lil, will serve them up to us at the appropriate times, and we'll pause a couple of points during the evening as well to answer questions as well at the end. We should have a space. Often we don't get to answer all the questions because we can get hundreds or dozens and dozens, and time runs out very quickly. And so you can visit learn.itmasters.edu.au, which is where our short courses are hosted. And in the forums there'll be chat rooms where people can actually discuss various questions that they want to ask of each other. And Jeff and I will no doubt pop our heads in from time to time as well. Before we start, I'm webcasting, as it were, from Melbourne. And I'd like to acknowledge that we are webcasting from Woy Wurrung country, the lands of the Wurundjeri people, and I wish to acknowledge them as the traditional owners of this land. I'd also like to pay my respects to their elders past and present, and Aboriginal elders of other communities who may be present today with us virtually. And now I'd like to introduce our team for the evening, for the next 4 weeks, in fact. On my virtual left, and I'll see if I can switch him on, is Dr. Jeffrey Jenkins. Jeff is a senior engineer at a company called Core Wireless here in Melbourne. And in fact, all over the world, they're an American-based company who provide connectivity services for IoT application and device providers. He's been there since 2007, roughly now. That's a long time, isn't it, Jeff? And prior to that, worked for Telstra, which is our local carrier, for those of you from overseas, in similar fields. He will give us some of the technical rigor that we need throughout this series, and we'll take the lead in presenting weeks 3 and 4, which will be more focused on the nuts and bolts, how everything works. My name's Shane Murphy, as I said before, and I too have a long history in the Internet of Things and its predecessors, working first in two-way radio comms in the 90s and then in cellular applications in the 2000s. And I moved to IT Master a little while ago. But my background's more in the business and project side of IoT. And so I take the lead in presenting weeks 1 and 2, where we're going to focus as much as we can on the why of IoT and the how, not the what, and not the what how, if you like. And Jeff's going to keep me on track with that. And Lil, as I mentioned before, our moderator, is here to keep us herded and in line, because it's very easy to go overboard. Jeff and I have worked together in the past, so we have quite a lot of war stories that we can contribute to, and I hope you'll find those interesting. Hi, Jeff, by the way, welcome aboard.
Thank you very much, Shane. It's great to be here, especially with this international crowd from just everywhere. It's fantastic, isn't it? And a few other languages and English cropping up there, which it's good to see. And I also would like to pay my respects to the Wurundjeri people. And I'm glad that we do that.
Excellent. Now, in terms of plan, we're going to generally examine what the Internet of Things is in week 1. We'll talk a little bit more about that, where it came from, where it's usually made up. And I'm going to put this in here, but Lil will be reminding everybody multiple times. Next week, the course is going to start 1 hour earlier if you're viewing from outside, if you're not in Victoria in Australia, New South Wales, Tasmania, or South Australia. All the other places in the world will be 1 hour different in time, because we move into daylight savings. We normally try not to put our courses in the middle of daylight savings, but we got caught this time. And so just remember, next week, if you're viewing it at your local times 10 o'clock, it'll be 9 o'clock next week. It's UTC plus 9 o'clock next week. This week, it's UTC plus 10. We will remind you again at the end. So, yeah, please put that in your diaries for next week. So that's week 1. Week 2 will be more about projects. We'll discuss the business of IoT, if you like, why it makes sense, how it makes sense, and how to create successful projects to a certain extent. And in both weeks 1 and 2, there'll be lots of examples of projects that have gone well and badly. Yes, and not Queensland, unfortunately, for the daylight saving. Weeks 3 and 4 will be primarily led by Jeff, and I will be just hosting, and he'll focus on all of the details of things, you know, how the pieces fit together, why particular technologies make sense, and how to assess them, with a focus in week 4 on things like big data and results and applications side of things, whereas week 3 will be more about the actual communications and the devices. So, with no further ado, let's launch into some actual content. This is what we're going to cover this week. And it looks like that. Fortunately, we'll just talk about what is the Internet of Things. This is a very, very introductory week. And here are our pictures, by the way, and you can choose which one you want. I'm the bottom picture, of course. What drives IoT take-up, as I said, IoT device and comms, big data and applications. That's our things this week. History, what happens, you know, where it came from, because the Internet of Things as a concept has only been around, well, it's actually been coined about 25 years ago, but it's still only been used widely for the last 10 or 15 years. The major elements of a system, how they all come together, we'll talk a little bit about those, some examples of IoT apps and why people use IoT. So it's going to be reasonably high level. and it's going to have a lot of generic information this week around what's going on and what has happened in the past. So let's start with the definition. And it's always good to read an actual like Wikipedia style definition. The Internet of Things, IoT, describes devices with sensors, processing ability, software, and other technologies that connect and exchange data with other devices and systems over the internet or other communications networks. Now, that is very broad, but it actually does cover all aspects of it. And you'll see more when we get into some actual diagrams of systems. The term was actually coined by a Procter & Gamble engineer, or in fact, computer scientist, Kevin Ashton. He was looking at putting some of the early RFID tags on products so that he could track them through a supply chain. He said, oh, this is like the internet, but it's things. And somehow that name has stuck. And we'll talk about the names that came before it. The whole concept of it, though, is that no humans are involved in the day-to-day operation of the IoT network other than to receive outputs. And Jeff will talk, I'll pass it over to Jeff, talk about that in just a sec. But you'll also hear other terms bandied around. There's the Internet of Things got quite a Guernsey recently. I'm not sure that I can really differentiate that from the Internet of Things particularly. I think somebody had a substantive interest in differentiating that. There's the IIoT, the Industrial Internet of Things, which sort of focuses on a subset of the Internet of Things that we'll cover off a little bit later on, which is more about monitoring machines and devices in that sort of original applications of where IoT came from. And again, that's, it's deployed by people that have an idea that they want to focus on, so they come up with another name. But Jeff, let's tell me about why humans aren't involved. We're getting people asking, hang on a minute, I think IoT involves smartwatches. Oh, humans are involved in that.
Actually, I'm looking back at that definition, Shane. I read it a couple of times, and it captures something and maybe misses something a little bit. Obviously, Internet of Things involves something. In this case, usually a sensor, something that can convert an observation, a temperature or the like, or a location into a network message, and then pass it over, share it with something else in the system. And so that says there exchange data with other devices and systems. But the focus becomes very, very much on exchanging data with systems. And so we get a sort of stack, a hierarchy, devices, sensors at the bottom, some communications, something in the cloud, and then somebody watching it. And that's the stack that we'll talk about later. One of the interesting things about no humans being involved, and this is true and false, is that when we try and work out what the value of Internet of Things is, what the value of these projects might be, sometimes because people are not involved, the value is not recognised, and I think this is largely true in the history of the Internet of Things. So we often at work we are often connecting important devices, gathering very important information, but the customer says, well, there's no people involved, it's just a few things, and we're not going to pay much for the communication. So getting away from that, I think, is one of the purposes of this course, to recognise the value of Internet of Things designs, and to work out how to exploit that value, how to build projects out of it.
Yes, and I think you'll hear what you might even call a jaded or cynical view from me at times, because I have heard more pitches and propositions for Internet of Things applications than most of us have had hot dinners over the years. It was part of my job to listen to people's business cases, and to be honest, the overwhelming bulk of them were absolute rubbish. And that is why so few things actually got up in the early days. So we'll talk a lot more about that sort of stuff in week 2. But referring back to what...
to be honest, Shane, pardon me intervening at this point, but a lot of those suggestions came from me.
Yeah, well, I wouldn't say that. But yeah, going back to what you're talking about in terms of a diagram, this is a diagram that I've come up with because I've tried to simplify it reasonably, because I think every time we start talking about layers and this and that, it makes things slightly more complicated to my small brain. So basically what we have here at the left-hand side, we're going from left to right across this set of diagrams. And what happens is events happen, measurable stuff happens. An ambulance turns on its siren, starts moving, somebody starts up a machine, they pour some concrete, it rains, a shark or an orca moves around, the fire, the fire hydrant goes off, there's there's electricity transmitted over electricity lines, a gaming machine plays, they're big users of IoT, a photocopier tracks the number of photocopies it's got. So all of those things, they're events in the real world. And then the IoT system sort of starts at this point down here. I should have drawn a line in probably. And what happens is there are measurement sensors of some sort or interface devices that interface with these things. We call them edge devices, but essentially they measure what happens in some way or another. That measurement can be a flick of a switch, it can be an on and off, it can be a temperature, it can be all sorts of different things, but essentially they are a device that measures something that happens in the real world. And then it goes into essentially the virtual world. It's transmitted across clouds, and we've all seen lots of cloud pictures, but the cloud can consist of cellular networks, two-way radio networks, satellite networks, fixed line networks, wide area WANs of various different types, LoRaWAN, Sigfox, all the old ones, and personal area networks like Bluetooth, Zigbee, all of those sorts of things. Then from there, it pops out the other end into a database and server, and a big warehouse effectively of data is what I would call it. And that's where big data, if you like, sort of raises its head as a concept, because these data warehouses keep enormous amounts of data. And as we go on, we'll talk a little bit more about that too, and all sorts of different implications of that data. And then from there, we get applications that go across that and deliver an output. And those outputs, in my head, are still remarkably simple, and they usually fall into three categories. The first category is some sort of an alarm goes off. Oops, something's gone wrong. You need to know about this. That requires action from you. Or you get a report. These are the things that happened in this period of time. Some of them are more important than others. These are the important ones. Do something about them. Or we get a transactional event occurring. And they're essentially all of this that boils down to one of these three things. And I'd be really interested as we go through the, even if people have examples of things that you think contravene this sort of way of looking at it, because it is a fairly typical way. And I think to sort of emphasize that, let's look at some other people's concepts of it. If we go back to the basics, we've got edge devices, as they're called. Usually the communications network, a database server, and then an application that overlays that, which produces an output. Now down here, and I think you can read that reasonably well over the slide, that's something from a company called InterviewBit, and they have a 4-stage IoT architecture. They call it layers. They have a sensing layer, a network layer. So the sensing layer is the edge devices, a network layer, which is your communications, a data processing layer, which is your database servers, and then an application layer. I call them smart apps, or process information, data transmission, data gathering. What everybody forgets to put is that out of the application layer spits outputs, results, things that matter. Otherwise, why are we doing it, for God's sake? They are the important things. Every part of it's important, but this is where the money is made. This is where the reason happens. And I hope you can see my mouse spinning around it madly, because that is what drives the application essentially. And this over here is what IBM do when they've got something that they want to tell you about, and that is an IBM version of an Internet of Things map. And I thought that Jeff might have a few things to say about that, because it's quite a complex beast.
I did want to, Shane, but just before I do, over on the left side, what you just talked about, is changing dramatically in its architecture and design and in what it's capable of under our feet as we speak. So the smart application layer has become much smarter in the last short while. And that's one of the things that we're going to have to address in this course is artificial intelligence or machine learning and IoT, is that just going to be not require the humans anymore at all and just operate on its own? And what we've discovered as part of that process is that there's much more opportunity to do good things with the data than we ever realized. Not just aggregating it and passing it on, but processing it and understanding it. So actually, that diagram on the left is rather like the diagram on the right, except sort of put on its side. And it's a little hard to see because the writing's small, but what you've got in those vertical layers, vertical towers, actually vertical silos, they almost are, is 4 networks. So you've got over on the left the proximity network, so that's your data gathering, it's that lowest level, the devices themselves. Then you've got a public network, and that is the comms to communicate the data across to the third silo, which is the cloud network. It's the most complex one, as you can see, at least in IBM's understanding of it. There are lots and lots of components there which are performing special operations on the data before it is passed over to the enterprise network on the right. So we might think of all of that as one big network. They've split it into 4 networks with all their individual complexity. And so we're going to have to visit that again. But I draw one point to your attention before we move on, and that is look at that across the bottom. So that's the security element. And you see it's oriented in a completely different direction. Each of these vertical blocks operates independently, but the security element traverses the whole lot of them. And that's key to the design. We'll talk a lot about security as we go along. And that particular way of thinking about and representing the importance of security as that which binds everything together is something we'll talk about again.
Absolutely. I thought we might also pause here for a couple of questions before we move on, because we've got a few here. Jeff, I thought you might know the answer to this one. How are IoT outputs related to big data? Maybe that's something you'll go into in more depth in future weeks.
Yeah, we'll look at that, I think, in week 4. But when you think about an IoT project, it is a way of taking, accepting data whenever it comes. So you don't have a human there watching all the time. You don't want to miss any of the outputs. So you're going to have to put them somewhere. You're going to have to store them. But as the amount of data increases, and more especially as the complexity increases, so we're getting data from 5 or 6 or 7 or 8 different types of sensors, perhaps, and then we want to be able to see how that data combines into a single understanding of a situation and abstraction. So we might, for example, we might be collecting some traffic management data. And what we would like to do then is we'd like to also collect weather data, because weather and traffic are closely related. Bring those together into a single system of big data and operate on it with some machine learning and artificial intelligence to draw the conclusions that we can then pass over. So the data is bigger because there's so much more of it, but also because it's more complex. And then the way we analyze that data, the way we dredge down into it, adds complication and adds sophistication to the way our IoT system works.
Exactly. The other question somebody's asked here, does Bluetooth also count as a network for IoT? It does indeed. It is one of the PANs, the personal area networks, and I think I might have passed it by when I mentioned the PANs. By the way, for those of you interested, Jeff's background is ancient Greek, and he's in fact a doctor of ancient languages, and hence that is a bit of a papyrus, Jeff, that you've been translating, that you've got on the wall behind you.
Yes, that one is a 3rd century text from Egypt, which I didn't actually excavate, but I was sitting in the dig house when it was found. And they came back from the morning's excavation all very excited, and they said, look what we found. They had no idea what it was, of course, but because they were archaeologists, but it turns out to be a very important and interesting text, and I like to have it as a reminder of those days.
In fact, I think we have a photo, anybody who's logged into the learn.itmasters.edu.au, from that dig of you and some others standing on a mountain or a sand dune. Anyway, back to the questions, then we'll move on. One more question. What is an example of transactional output? We will actually give you a few examples later on, but things like parking meters, FPOS, ATMs are all examples of transactional outputs, but we'll talk more about those as we go along. So moving along, we're now into how did IoT come about? IoT has been called all sorts of things over the years. One source that I read a little while ago had it beginning in the mid-1800s with the introduction of the telegraph, enabling some autonomous messages to be sent over those wires. You know, a switch went on, they would get a bit of information back. That's probably drawing a very long bow. I think if we talk about, you know, the 60s, 70s, 80s as being the real start of it here in most countries, that's when things like radio networks became more affordable and governed, and you got more widespread electronics out there that could do things. And then what happened was, in the beginning, they were using fixed line phone networks. So Telstra, for example, here in Australia, and I'm sure other carriers in other countries did the same. They had piles and piles of private fixed telephone cables. Many of them were only used directly for what we call telemetry systems in those days, and others to operate radio networks that sent data for telemetry and SCADA applications. So the phone networks would be hooked up. So you'd have something like that big bank of switches over there, and they would all be wired to particular machines, and the machines would send information. I'm getting over hot. I've got, you know, a gauge would say I've got to a hot point, and it would flip an analog switch, and that would set off an alarm on this huge network of bank of things. What then happened over a period of time is that SCADA became an acronym, was called Supervisory Control and Data Acquisition, which is a terrible acronym. But SCADA has been around for a long while, and it's a computer-based system for gathering and analyzing real-time data to monitor and control equipment that deals with critical and time-sensitive materials or events. These sort of took off more so in the 70s and 80s as PLCs and microprocessors became available and were connected to fixed line networks initially, and then to radio networks to monitor things like, they started off in places like large factories and oil refineries. We had very high value pieces of machinery there, and with lots of consequences if things went wrong. That's the real gist of it. You know, if something goes wrong in an oil refinery and it blows up, you have major problems. And so you want to know about that stuff in advance. So you went from those sorts of banks that you've got on the left to more displays as Windows came on board, and you could actually put things in color and have some sort of graphics where you've got information in red, yellow, green. Traffic light systems came up, where still though, with all of these, you have very skilled engineers running the networks, and they're the only people that can really make head nor tail of what's going on with them. It's not very user friendly. It's not, you know, it's not simple. It's very techy. At the same time, people like water utilities and the like would start also putting data acquisition devices into things like flow meters for their, and level controls for flooding, or to make sure that the dams weren't bursting, all of that sort of stuff. That's essentially what happened. Then as the 80s wore on, you got more of them on specialized two-way radio networks, as well as cables, and you got standards. Originally they ran on those huge monster computers, and then eventually moved to PC-based graphic display systems in the late 80s, basically, and more so even into the 90s. They also connected a lot of devices up to wide area paging networks for alarms. It was one of the first demonstrations, actually, those paging networks, of a wide area public access network being used for Internet of Things type applications. But in those days, it was called telemetry or SCADA. And then we moved, as we moved into the 90s, the name changed a little bit. Still called telemetry, also called telematics, which was a branch of telemetry, seemed to take it over for a while. But increasingly, it became wireless-based, radio-based. But you still had these problems because it was usually being sent over two-way radio systems, which would be able to send data at a speed of 1,200 bits per second, which is really slow, which meant you could still only send very small bits of data, and it was expensive to do because each radio device might cost you $1,000 to $2,000 to $5,000 per device to actually buy and install it and set it up with the sensors, and then $30 or $40 more a month to actually use that device for very small amounts of data. And they were sharing radio channels, so you got contention between the way that it worked. Because if two radios transmitted at the same time, it just couldn't handle that and would lose the data. So you had low data speeds, contention, fixed cost per month. Data dispatch started to happen over this period of time as well. We got people like taxi systems. You would see, if you remember back that far, the first little black boxes that sat on top of taxis, and they sent out where to go for the taxis. And some courier systems started to appear in this as well, usually only at the top end of town, because the devices and the cost per unit to use it every month were very expensive and they couldn't be justified. You'd be spending hundreds of thousands of dollars setting up systems. I do remember, for example, in the late 90s, 98, 99, a system was set up here in Melbourne for one of the transport companies that had a just-in-time delivery service for Ford Motor Company. And I think for 25 devices and the whole system, they were spending about $200,000 or $300,000 and about $2,000 a month. And to be honest, the transport company told us that they didn't actually use it. They just had to tell Ford that that's what they were using, because Ford wanted to be seen to be doing things right. So you've got this sort of tension between commercial organizations that sort of want to do stuff, but only if it's really cheap, and a growing desire from customers demanding it. And in the middle of that, you've also got government bodies that are starting to regulate as well. And that's why you've got much more environmental monitoring by government bodies or non-government organizations like utilities and the like. Then, we'll just go back up there. Go on, Jeff.
Shane, the SCADA origins are really interesting, aren't they? Because these original systems were quite complex and quite capable. And what you say is true. The only limit on the number of devices and the amount of data you could collect had nothing to do with the machines. It was the actual cost of the devices. And so that idea that someone would be observing something in a factory and then would ring up the boss and say something's gone wrong with number 6, that was so slow and really in many ways unreliable. All of that could be replaced on a grand scale with one PC in the factory talking to multiple machines. But it took some clever engineering to achieve it. But it started as a very complex process.
Yeah, so lots of companies that made their money out of selling small radio devices for about $2,000 each that had some inputs on them, and they were usually analog inputs at the time. But we saw growing digitization throughout the 90s as well. And of course, then along came the first proper cellular networks, as in they were digital cellular networks. The analog networks of the early 90s weren't much used for telemetry and IoT. There were probably applications out there, but we didn't see a lot of them. But first what happened with GSM is that we got what they call GSM dial-up. So that was just like an old modem dialing up over the phone into the internet, and worked in the same way, but at an even slower speed. In theory, GSM had a speed of, I don't know, 32 bits per second, but it was more like half that as a realistic thing. And the biggest application of it that we saw, the only time it was really deployed properly here in Australia, for example, was in electricity meter reading. And we'll talk a little bit more about that case study later on in the day. But essentially, in Australia, there are in excess of 50,000 dial-up meter readers in operation by about 2000, 2002. What they actually did was a big dialer would actually dial every single meter every night and download the data from that business's usage during the day. And as I said, 50,000 dial-up meter readers. So it had to have a business case. It had to make sense because it was happening, and it's government bodies that are driving that sort of take up by them. So you sort of get to the end of the 90s and everything's on a bit of an edge of things seem to be happening, but they're not quite happening. I do remember starting in this field in cellular in the early 2000s, and every app that we conceived of back then has slowly come to pass now, but it has taken nearly forever to get there, and much longer than what everybody thought. We always used to talk about the J curve. It's all just going to go suddenly crazy. Well, the J curve's never quite happened. It's more of a slant, more of a slash, but it has had consistent, very strong long-term growth right across. So you're talking about compound growth rates of 15 to 25% over an extended period of time. So it has continued to do all sorts of things. And it's in the early to mid 2000s that things really start to take off, because what you get then is the introduction of SMS. So SMS was always there with GSM networks, but realistically, SMS was only suited to certain applications because it's very small data packet size. It's also send, store, send again, so that you couldn't always depend upon the timing of it being accurate. And we can talk a little bit more about that if you want. It's a store and forward technology rather than a straight through technology. And the other real limiting factor with SMS was, in the early days, SMS only worked over one network at a time. So until the networks decided to get interconnected, which happened in this country in 2000 and in other countries around about the same time, maybe in Europe a little bit earlier, certainly in America much later. And once the networks became interconnected, the volume of SMSs went from that much to that much overnight, almost immediately. And so that did help because it factored in the ubiquity of the platform, but it was still very expensive because SMSs in those days were costing 20 cents each. So it was costing you 20 cents every time you wanted to find out where your vehicle was, for example. Is that a business viable proposition? Who knows? Sometimes it was, often it wasn't. GPS was the factor, GPRS was the big factor that actually really fired the explosion along. Because what would happen is you then have IP-based platforms that come into it. Data is sent in a much more sensible way with no real limit on how much you can send over a period of time, even if the throughput's not very fast. The throughput on that was up to 64K, but it was more like about 30 to 40 on average. And the costs slowly came down as well. And we'll talk a little bit more of those costs. But if you look at it in terms of cost comparison, at one point we were comparing the cost of an SMS with the cost of GPRS, and it was essentially something like, I think it was either 100 or 1,000 times more expensive on a per byte basis to send something via SMS than it was via GPRS, if you could just be charged for each individual byte. And that's why SMS applications only work in certain areas. Usually they work in applications where you want to find out about something and it's really important, but it's not completely mission critical. Although in the early days, a lot of the early tracking applications came from South Africa, where security was paramount. And the basic construction of the network and the way that GPRS works is pretty much remained the same ever since. And it's the idea around GPRS is that effectively you're running what is analogous to a virtual private network across the radio network with data. So everybody's data from GPRS goes down a particular pipe, if you like, a virtual pipe where it's protected from other people's data, and it can only come out the other end in a particular way. And they do that by what they call access point names in GSM. It was done slightly differently in other networks, but essentially access point names are analogous to VPNs. And you would, in the original days, in the 2000s, you would pay a lot of money to connect a cable into the headquarters of the phone network, and all of the data would come down that cable back to your servers or your office or wherever you wanted it to end up. Now, of course, that has changed over time, and VPNs from your premises, virtual connections from your premises into the networks are now the rule. And then the other thing that really changed, and from a cellular point of view, that opened things up in that period, was roaming, global roaming. And it's where the Americans shot themselves in the foot with the way their networks worked. And we'll talk a little bit more about that as well, because once you were able to take the same device with the same SIM card most places in the world and have it work, it changes the whole basis of what you can do. It means you can manufacture devices that will be used anywhere in the world. So you don't have to manufacture a specific one from Australia and a specific one from Malaysia and a specific one for Nigeria, because we're all using different devices and networks. And they are huge factors in the ubiquity of the systems. But Jeff, you can tell me about what happens once we get past GPRS, because there's been a lot go on since GSM finished.
Yes, there has. And in actual fact, we're about to be out of date with our reference to 3G, 4G and 5G, because as most people from Australia will know on the call, we're closing down our 3G networks as of middle of next year. And there's quite a bit of close down has already happened because of refarming of networks. Sorry, Shane?
Oh, I was going to say, we already went through that when GPRS and GSM closed down. And it was interesting because if you look at the timescales, GSM lasted, 20-something years out in the field in use. 3G's lasted, actually, it's probably nearly 20 years now as well. I suspect that 4G and 5G won't last anywhere near as long.
Yes, yeah. And the other big and important difference, of course, is coverage, because these networks are bigger, and so particularly if we're talking 5G, then we're covering a lot more territory where there aren't many people, but where there might be very important IoT applications. I was going to say, Shane, about SMS and GPRS, that very consideration that you've outlined there already still exists to this day with, say, Iridium. So Iridium, we use Iridium short burst data quite a lot. It's just like an SMS, really. And in actual fact, it's charged for by the byte, because these networks are so expensive to put up there that they've got to recoup their costs in various ways. Charged for by the byte, and short burst data costs roughly $0.01 per byte.
Wow.
Round figures, but that's dramatic when you think about it. And we've had Shane and I have had our experience of this, where we had a customer doing Iridium short burst data, and they had a complex device. It was a hybrid device of GPRS and short burst data, and they got all the channels a bit confused, and they started to send their GPRS over the short burst data. If we hadn't noticed, and it took us a few days to notice, then everyone would have been bankrupt at the end of that. So I wanted to just mention that we might say something about satellites, or I'll go back to you for that, Shane, but to introduce it at least. But what's happening much more is that these cellular networks didn't really make much of a distinction between, once they did data, then they didn't make much of a distinction between the types of data that they did. Large data might be VoLTE, so voice call by data. It might be it might be something like website delivery, or it might be exchange of IoT information. Now that's starting to change, and with 4G and more particularly with 5G, IoT style data connections, which are subsets of the whole data capability of the network, are coming into play, and this is particularly so that power management can be applied, and we'll talk about that in week 3. But for other reasons too, sometimes including security and separation of channels. So all sorts of complexity is coming in terms of IoT on 4G and on 5G. And NB-IoT is a separate, is something separate. I wanted to mention one other thing quickly, and that is bidirectionality. We've mostly been talking about collecting data from devices. It comes into the server and then somebody looks at it. But we should also be talking consistently about information, control information going out from the network home, out over the network to the devices. That might be saying to the device, don't report so often, you're costing us a fortune, or today is a hot day, we want more frequent reports, those sorts of controls. So that's the bidirectionality, which is critical. And Shane will remember how much hassle there is in getting bidirectionality in SMS systems, because the channels are completely independent.
Well, it becomes critical in some applications because they were, without bidirectionality, you have what's called a truck roll if you want to fix anything. And that is very expensive when you get into truck rolls.
Indeed, and that'll be, I'm sorry, Shane, one more thing, just quick, is that'll be when we talk about engineering aspects later, designing these things in at the beginning, knowing what the capabilities are and making sure that we exploit those capabilities for best functionality. That's an important engineering function. It's the original design of the project, and it's the key thing you've got to focus on.
Excellent. Yeah, I think you could say the summary of this period is that 3 or 4 things happened at the same time, because you have also, as we said, dedicated satellite networks coming out, which gave you a lot wider area coverage. Anywhere on the globe pretty much was covered, as long as it was outside and in view of the sky. But what generally, and it is a feature of the satellite networks, that nearly all of them went through what they call in America a Chapter 10 or Chapter 11 bankruptcy or insolvency procedure, because they spent so much money getting them up in the sky and took so long to get uptake that the only way they could actually make money in accounting terms was to put them through insolvency and then come out the other end with all the debt having been wiped, and then they could make an ongoing business out of it, but they were never going to recover their capital costs. And to be fair, in the early days, cellular was not dissimilar for quite a long time. It took a long while to get the cost factors up. But what generally happened, though, is you've got converging things during this period, which is you've got wider and wider coverage. You've got more and more devices that are built the same way, and costs come down, both of the devices and of the data that you're sending. So that's really important. And that leads us on to the next thing, which is there's a whole pile of other technology that enabled the IoT revolution. It didn't just happen because a couple of people made a few things over a period of time, and it didn't happen because some organization like Ericsson or Nokia, who built most of the core cellular networks, for example, decided that they were going to do the Internet of Things, and therefore they had to make things happen. You had a convergence of all of these things happening in the same sorts of time periods, and they became enablers for it. Obviously, the first one is Internet Protocol. Without that sort of addressing and ability to send and transmit data in those ways using those systems, nothing was going to happen. Obviously, without the internet, without IP, the internet doesn't happen. But it is worth reminding ourselves that these things happen at the same time. GPS, global position systems. We take that so much for granted now, but in the 90s, GPS had what they called the wobble factor. It was built for the US military. The US military deliberately or fuzzied up the results that you would get from the devices in order that the Iraqis couldn't fire back at them, basically. That was because it was developed around about the time when it was tested during the Gulf War in the early 1990s. And so therefore the American military prevented accuracy in data. What happened then over a period of time was everybody found ways to backwards engineer the algorithm that the Americans used to make the wobble factor happen, because it would put your results out by 100 to 200 meters often. And people found ways of making them more and more accurate, even allowing for that wobble factor. And so the military eventually said, oh, well, yeah, we've shot that bolt now, we might as well just accept it. And they turned that misinformation factor off at some point. I forget when it was. I think it was in the early 2000s. But, GPS was a huge development because it underlies so many other things that we do, because you do something, you have a measurable event and you assign a location to it. And in line with that is digital mapping. In the early 2000s, you had to pay $40,000 in Australia for an Australia-wide mapping license, and even then, it was of hugely variable quality. The digital maps worked really well in some areas, and in other areas they were non-existent, and you got a patchwork of maps from different suppliers. Now, digital mapping, Google, it's all there for pretty much free. If you make commercial use of it, you pay a license fee, but it is all consistent. It's regularly updated. They have cars driving around adding, photographs to it. So that is a fantastic, those two things together are amazing things. And you talk about big data, there's been questions about big data all night. Those are part of the big data revolution, being able to have location data attached to any event that happens. The other things that happened was that you got large-scale database structures, and SQL is the one that tended to be the winner out of all of those, because there were free versions, freeware versions, there were paid versions, but essentially SQL was SQL. It all had different things, and people didn't like using other different types of SQL, but it tended to be the sort of system that people settled on for making an Internet of Things application, because you could scale it up to quite a big size. And at the same time, it wasn't horrendously expensive. I know that, a lot of the bigger ones that the utilities use will use much larger and more expensive things like Oracle and other proprietary databases, but SQL by and large has been widely used, and we're still using it today. Miniaturization is really important for a whole pile of reasons. It brings down size, it brings down cost, it brings down power usage. Power usage is something we just can't emphasize enough, because when you have a device that's out in the field by itself somewhere, if it uses too much power, the battery goes flat, or it has to be plugged into a power outlet, which means a remote thing's not working. Power is power. Battery technology with power are two of the other major things that drive it during that period of time. Then you had all these other little operating systems. What I call WINS, or Windows CE, Windows Compact Environment or something like that, and other OS systems like the Palm Pilot things for small devices, both proprietary and open, made a big difference, because it meant that you didn't have to have as big a computer chip on the devices in order for them to work, and you could put some intelligent applications into them. And then at the same time, you've got continuing increase in chip capacity and decrease in power use at the same time. So all of those things factor together because they're happening roughly at the same time. And every few months, there's a bit of a leap. It's a bit like Moore's law. You get, well, obviously the chip capacity is Moore's law. Thank you, compact edition. I used to call it WINS because the devices were actually so unreliable in the early days. That's what you did every time you saw one, was go, WINS. But Jeff, you're going to talk about battery tech improvements. Are you back with us?
I'm back. I'm sorry about that. I'm in Sydney. That must be the problem here, I think. Bear with me. That the battery issue is very important, and we'll make a distinction in future weeks, already tonight, between a powered device and a device that has a battery. I'll take my example from CAD M1 trackers, we've got one that we sell quite commonly from Telstra. We'll have a little bit of a look at how it functions. It's got a 5-year battery in it, or if you make it report often, because you can control its reporting functions, then it might only last a year. But it's designed to be a 5-year device. Many good applications for a device like that. And then Teltonica make one which attaches direct to your car battery. It can report a whole lot more. So that distinction is really important, and especially the way it plays in with cellular networks as well. So basic distinctions here as this tech evolves, so it spawns new opportunity and segments itself into that new opportunity as it goes along.
Battery had other things as well. Oh, sorry, power usage had other implications as well. BMW told us in the early days of vehicle trackers that were using SMS that they could virtually weld off the power that was required to run the things. And inevitably, whenever they tested a new one, that the car would go flat overnight because they had such small spare capacity on the power rail from the battery. And it was not until the early 2000s that they could get a vehicle tracker that didn't flatten the battery on a BMW, which was, of course, this market segment that really wanted vehicle tracking for security and anti-theft in those days. The other things that happened were, as we said before, cellular ubiquity really, once you've got one network that covers nearly everywhere, that changes the ball game. In the early days, you could only have two-way radio networks covering a very small area. They expanded them a little bit, but you could only usually get it at most a few hundred square kilometers. Cellular, as it rolled out from just cities into wider and wider areas, made all the difference. And again, as I said before, it's where America sort of shot itself in the foot, because in the early days, America had a different phone network for every city, and they weren't interchangeable. You couldn't roam from network to network with ease. We were aware of a businessman from Australia who used to fly there with 48 phones in the back of his plane because he had to have a different phone in every city. And of course, that meant that, you couldn't actually have vehicle tracking work very effectively in that environment, certainly not over cellular. And the other enabling technology is cloud servers, because if you're going back and you're having to spend 20, 30, 40, 50, $80,000 on physical server infrastructure, and then have people like Jeff visit them at all times of the day and night to turn them on and off and install software and upgrade things, which is what happened all the time, that's a lot different to being able to just buy a slice of a data server from AWS or one of the other suppliers and have things just work for you. And more, the cloud is really becoming the cloud, whereas before the cloud was something that was kept either in the back of your office or in a data center if you were really lucky and spent a lot of money on it. I thought we might...
Dynamic scalability is the key to that, isn't it? As everyone on the call will be familiar with this, that you only buy what you need, and you only have to plan a week ahead.
Absolutely.
And if you're very successful, then no harm done. And the one thing to say about cellular ubiquity, Shane, is that this is producing all sorts of hybrids. So you get the backhaul might be satellite, a local network might be Bluetooth.
Yes.
And your node is smart enough to be able to combine a whole lot of information and ship it back by satellite using exception processing and all sorts of smart stuff like that. So we're bringing these various technologies together in various constellations to produce the benefit.
Now we're wildly running out of time, so I think we will just quickly rush through a few slides on the uses and everything, and then we'll get some questions in at the end. Lil has just closed the questions, I can see, and we don't have a pile of questions, but we've got actually still about a dozen slides to work through. So essentially, if we're looking now at the users and the uses of IoT systems, we divide them up into a few areas. I mean, there's all sorts of different ways you can divide them up. This is just one, and I will reiterate that our course this week is really, it's a short course in that, we're trying to cover a lot of IoT stuff in a 4.5 hours or 5 hours of talk time. And that we do have a subject at Charles Sturt University called ITC 560, the Internet of Things. So if you're interested in actual postgraduate university subject, that's a good place to start, because that covers all the stuff we're covering in more detail. But we're going to give you as much as we can during this. So forgive us if we forget things, for example, like, solar panels on batteries for external devices and stuff. There is so much thing that happens on. But yes, if you're looking at different users and uses of IoT systems, there's a group that I call environmentals. It's people measuring rivers, dams, lakes, sea salinity, tidal waves, fire floods, weather stations, contaminants in the water for dams, all of that sort of stuff. And Jeff, you've had experiences with disasters.
Yeah, I've had a few disasters in the wild. Environment is so much the key to that, and so much and so important for all our futures, isn't it? To be able to measure weather accurately. We've got a project at work which is involves a large device about the size of a small car. It has the ability to float down to the bottom of the ocean, and to measure the salinity of all the ocean around it, and to map the ocean currents. And then a big ship comes along every now and again that floats to the surface, and the data is read off. And that's an IoT system, very complex at the monitoring end. Quite a basic process for collecting the data, and the analysis of it, again, very sophisticated. So it's intriguing how those various elements of what constitute an IoT program can be more or less complex.
Like cows with necklaces, as
yes,
you say,
yes,
or pendants.
And sharks, Shane, you've got a picture of the shark, and some of us are a bit familiar with this. It's a satellite-based tracking that tells people at the beach if there's a white pointer in the area. It's a bit hit and miss, unfortunately, but it's better than killing the sharks, that's for sure.
Wow. I quite like flake, but yes, it is better in theory, and they are protected, and there's a lot more of them around now, speaking as a surfer. But yes, and research includes all of these sorts of things. So there is a category of IoT systems that are done for pure research, and they're funded by universities and government, and they often contribute a lot to what goes on with IoT in the longer term, and particularly in these sorts of areas. The next sort of usage is what we call the industrial Internet of Things, or IIoT. Again, it's all of these machineries, monitoring power, gas, and water networks where security is critical, as well as reliability. And a lot of that is mandated by regulation. The electricity meter networks, if they fail to meter a certain number of meters every day for a certain period of time, then they actually cop enormous fines from governments, in particular in this country, for example. They're used for machinery, for efficiency, for maintenance, for effective use, and for security as well, to stop people getting into the machines. And buildings and services. We've got, security guys. Often a commercial building in the center of a CBD these days is harder to get into than Fort Knox, honestly. You have to sign in, you get a tag, you pop it against the pass reader, and they let you in. Airflow, lighting, lifts, a lot of that is about saving power by using those things more effectively and efficiently, directing hot air to the coolest parts of the building rather than just trying to warm up one spot. All of that sort of stuff has become more and more widespread, and in fact, the default basis on it. And we're now talking about things like digital twins of buildings, where all of those systems are monitored in a virtual map of the building. And of course, measuring for utilities, which we do have a case study on, but we might run out of time before we get to it today. I'll flip over to the next one, Jeff, which I was going to talk about, which is tracking. And I've been involved in vehicle tracking since the beginning. And obviously tracking is hugely important for a whole pile of reasons. It came out of theft and security issues. As I said, a lot of the original applications were driven by countries like South Africa, where vehicle theft was endemic and murderous. And some of the companies that we worked with in those days actually send armed response teams after vehicles that were stolen, often into neighboring Mozambique, for example, and they would then recover it at gunpoint and drive the car back and get it fixed. But obviously that only lasted for a period of time and only in certain circumstances. Nowadays, you're looking more at insurance. Is the vehicle being driven correctly? And mining companies actually monitor drivers' behaviors on those big trucks. Really important, because if they're grinding the gears on a $500,000 truck, that costs serious money. And they will actually retrain the drivers time and time again to make them drive in the correct way. We're looking at the condition of the motors, the gears, the systems, not just how fast it's driving and where it's going, but how the vehicle itself actually operates. All of those things grew from a very small base of what they're able to do to now essentially there's a plug on most cars where you can just plug in straight away and get access to the whole vehicle's electronic monitoring system. I've forgotten the name of it. Do you know the name, Jeff?
I do, but I can't remember it.
That's right. We'll no doubt talk about it later. Transactional. Do you want to talk about transactional systems, Jeff? Or are you still looking for the OEM bus or whatever it's called?
Yeah. ODBC.
ODBC, that's right.
So had to write it down before I could do it. Yes. So this is all the payment stuff and personal transactions of that sort, FPOS vending machines and the like. We had a lot of experience with this, which we'll talk about if we have time in week 3, where we really want to focus on logic context, because this type of application has a lot of important logic on the device itself. These devices are as sophisticated as they come, but we'll come back to that, Shane, for sure.
Yeah, these are all and the difference with these systems is that often there is a human involved at one end as well, but they're all transactional. The data flows in both ways, and usually money's involved in some form or another. You're purchasing a bag of chips, you're paying for your ticket on the train, or you're just taking money out of the bank. And in that case, money is the product. And you have to think about it in that term. An ATM is really just a vending machine for money. Health is a huge user of it, often driven by government regulation, but also driven by things like health insurance companies, particularly in the United States. Started out as remote monitoring for various conditions, like pacemakers and things. There are ways of downloading the data from pacemakers, more so where the person actually had to come in somewhere and have it downloaded. I don't think they transmit their data directly at the moment. We've seen asthma puffers with modems attached, sleep apnea devices, Legionnaire's disease. I've put that there because it's really about air conditioning monitoring to see that the Legionnaire's disease is not being spread by building systems. But it's become, health is the driver of it, and has forced huge change in the building industry about how they manage and monitor air conditioning systems and the pools of water that accumulate around them. Pill boxes for people that don't remember to take their pills, personal alarms. You were going to mention personal alarms, I recall, Jeff.
Oh, yeah, I might have been. When so many of these devices have a SIM card in them, and they're collecting data and sending it and receiving it, of course, because it's always tends to be bidirectional, and these are certainly opportunities, because the compliance level is high and people expect to pay for these things and they value their health, and so these are good business opportunities. And personal alarms, we have a number of companies doing that, and they're doing it on a global scale. So these are Australian companies who are operating in New Zealand, a couple of them in America. So this is a genuine opportunity in the space for a good design.
Absolutely, and contrasts extraordinarily well with pet trackers, which we'll talk about on another day. Wearables is the other one with health. You know, all of your Apple smartwatches and your Fitbits and things. Imagine the amount of data that the makers of Fitbits have got on the general health of the population now, and just keep that in the back of your mind for when we talk about security and privacy. Smart cities is and look, I've probably skimmed over a bazillion and three uses of IoT. But if you look at them, they all do come down to those 4 or 5 ways of doing it in one of those categories. It's very hard to find one outside of it. I haven't seen too many. Obviously, AI adds another flavor to it, but AI is really at the processing end more than anything else. And we will speak to AI a little bit as we go forward. But smart cities is designed really to combine all of the above. You have a lot of smart buildings, you have smart infrastructure, and then somebody is able to make sense of all of that data from a big data viewpoint and use that to create better efficiency for the city, more security for the city, better livability for the city, so they can monitor the air quality, for example, and provide warnings about it. They can turn the lights on and off better and control power usage. So it's just scaled up. It's everything scaled up into a whole urban environment. Now, what were you telling me before about that, Jeff, about how it hasn't really worked in quite the way we might have thought yet?
I'm struck by these really good questions, Shane. I'm distracted by a couple of really good questions I see in the chat. We'll be using those to feed back into our into future weeks. One of the things about smart cities was the inclination of government to focus IoT systems in one place, not to spread them around, but to put them in one place. So we had certain smart cities and all the rest of the cities are stupid. And that hasn't worked very well. What we really need is the wide distribution of these IoT systems, not all located in one particularly smart city, but making a contribution in every city to everybody's life. And so smart cities has been to some extent a failure. We've got some, but we're not sure anybody lives in them.
Not to the extent that we would have thought anyway. I think tonight we'll just do one case study, and I've got 3 or 4 more here and they're in the notes, but we'll actually talk to them potentially next week or certainly the week after. This is about sleep apnea, and sleep apnea started, and the rationale was to provide to doctors ongoing measurement of breath pressure and breathing patterns so that they could more accurately treat individual cases. That was the rationale behind doing sleep apnea IoT. You've obviously got the CPAP machines, as they call them, what are they called? Continuous pathway air pressure or something. And we were involved in one of the early designs of these where they added reporting back into the system. The parameters were coverage because they had to work in building anywhere in the country. It was primarily going into America at the time. The cost, it had to be not horrendously expensive, although already a CPAP machine was costing anywhere between $2,000 and $5,000 easily. And you also had the other thing overlaying it of medical approval and the medical profession wanting to be involved in it. So was that successful? And a number of these case studies will be successful and some won't be. And the big answer is on this, well, it actually nearly died very early on and it had a design flaw. Can you explain what happened with that, Jeff? That meant that 250,000 units had to be recalled and reprogrammed and sent back out again?
Yes. So that was an electronics issue. Two elements of the machine that were interfering with each other because of poor electronic engineering, so not just reprogrammed, but really redesigned and rebuilt. The board had to be redone.
No, I'm talking about the problem that they had with not communicating with the network. So what happened was we get a phone call that said, tell me, you've got these devices out in the field. You've had them there for a while now. Have you had this problem where about 30 to 40%, and then it gets up to 60 to 70% of them just disappear and we don't get them back again. Can you explain what's going on there? And we went, yes, we can. And we gave them an answer and they didn't believe us. And they went away and thought about it for 3 months and studied everything because they thought it was far more complex. But in the end, the answer we gave them was the solution to it. And it was a very simple thing that revolved around the way cellular networks function. And it was a programming flaw, really, rather than a design flaw, I suppose. I probably mislabeled that.
Yeah. But in particular, Shane, with devices that sit static in one location.
Yes.
And then they fall off the network and can't come back without a reboot.
Yeah, essentially the network has a register of all the devices on the network that are live, and the device knows that it's registered and it sits there because it's in one place and it can maybe only see one cell, or it sees one cell as a very dominant cell in the network, and it says, I'm on the network. And the network, if they reboot it, which they do all the time, very regularly, every time they do maintenance, they reboot it, that clears that table. So what you end up with a situation is where the device says, I'm on the network, but I can't send anything because I can't contact it. And the network says, that device doesn't exist, so I'm never going to accept any data from it. And then they sit there staring at each other. And the only things that break that cycle are if you move the device, because if you remember, cellular networks were designed for mobility and everybody to have to go and move around. And as you move from cell to cell, that registration table updates. So that solves the problem. But you've got a device that sits in somebody's bedroom and is never turned off because it's next to the bed every night, then it's not going to move and it's not going to reinitiate the network. So what tended to happen was that everybody would put in a little routine into their software that did what, Jeff?
Just sent a trivial report, just a heartbeat across the network to keep alive.
Yeah, and essentially it rebooted the device and made it re-report in, and everything worked. But they actually had to bring them back in because they had over-the-air programming, but they couldn't even over-the-air program them because the devices weren't on air in the first place. And so it was very frustrating for them. And but notwithstanding that, what actually happened was it was inordinately successful. This is still one of the few and maybe one of the only projects that I've ever seen that under forecasts the demand for the product by 100-fold. They came to us and said, in a very IBM, there's only 3 or 4 computers required sort of way, and saying, we think we'll do 1,500 of these. We think it's a bit of a passing fad. Don't think it's super important, but we want to spend some time doing it right, because they'd done some with two-way paging, 5 years previously, and that had sort of failed. At last count, how many devices do you think they've got now, Jeff? Is it 500,000 or 1 million?
Yes, 1 million, I think. It's up there, that many. And the point you made, Shane, which I think is so interesting, is the machine's quite expensive, but they ground away this important comms element till no one was going to make any money out of that part of it at all. So
absolutely, when you've got 1 million machines, $2 a month is $2 million a month. You got to get out there, and they have to have a model for it. So the reason that this worked, aside from that design problem, that programming problem, was that they had a demonstrable business model. Because what I didn't disclose when I was setting that up is that the reason that these were put out there in the first place was not really for the doctors to have access to the patient records. That was a factor, but it wasn't the driving factor. The driving factor was that insurance companies would not reimburse the cost of the units unless you could prove that you'd been using it, and therefore reducing your mortality risk. It was that simple. And so you had to actually show that you'd been using it 60-something days out of 90 across a period of time. And once that business model was in place, there was a real rationale, a real driver for that to happen. It made sense for the manufacturers to do it. It made sense for the insurance companies, and it made sense for the users because it forced compliance with the devices, forced them to use it. So it was a real virtuous circle right through every aspect of it. And that's why it was so successful. And on top of that, it was also well designed because it was a proper medical device and it was approved and all those sorts of things. So it was, it was a good product, and it had money behind it. And you always follow the money with these sorts of applications. And that is the theme of next week, which is follow the money. I think it's probably time now to answer some questions because we've got probably about 5 to 10 minutes left. And I'll stop doing that. And in fact, I will go down to the end, which is going to have the reminder on it. 1 week earlier next week. I'll say that again before we finish. But in terms of the questions that here, was there a question that you wanted to speak to out of the stuff you were looking at before, Jeff, when you were slightly distracted a minute ago?
Oh, yeah. This is Ray. Ray's put quite a few good ones in. Not so much a question, but IoT in health with artificial intelligence has been producing faster and more accurate diagnostic data than specialist medical staff. So that's part of that whole moment of change that we're facing now. That won't do away with IoT. It'll just bring IoT to the fore, and with more and more opportunity, because AI can deal with that data better than we can do that now. So it's a really helpful comment, and it'll direct some of our thinking in the next little while.
By the way, Ray's just reminded me I got it wrong. It's UTC plus 11 next week because we're going ahead in time, not back. So it's 1 hour later, not 1 hour earlier. I will just change that now. And please be reminded in theory, your outlooks, if you put a calendar in, should update it automatically. So it's 1 hour later next week at Sydney time, 7 o'clock, and different times all around the world, UTC plus 11. Somebody asked, Jeff, how much the contribution of geo-based satellite IoT networks have expanded the connectivity and scalability?
So this is I assume this question is about what happens now. We've got low Earth orbit satellites, which are the size of a shoebox and about the price of a shoebox as well, and that gives us so much more, so many more devices that we can connect, because the client tile is only tiny. It's not expensive. The difference is that we haven't got the coverage in terms of time, regularity, that we will need for that to be absolutely useful. But at the moment, very useful for anything that talks to us once a day with a few bytes of data. That's brought the cost of those sorts of applications right down, and it's starting to make a big difference. We've got 3 new networks that we're looking at work involved with that. So that we'll talk about that in future weeks, but that's definitely a big change.
What kind of data does IoT collect and represent, structured or unstructured? I would imagine the answer is both.
Yeah, the answer is both. Yeah, definitely.
Okay.
I mean, data has to be structured in the end, otherwise, at some point, otherwise you're just staring at it and not going to make any sense of it. But the way it's stored could be either.
Mm-hmm. Was the IoT communication channel encrypted? There's a lot of questions about security, which we'll cover a little bit next week. But was the IoT communication channel encrypted back in the early days? If so, how? VPN, TLS? I'm not sure that quite gets the point of it, does it?
No, it wasn't, and still isn't, to a significant extent. Just depends on the sort of data that you're sending. But our customers do IoT all the time, and that data is rarely encrypted.
Yes, it is.
To this day, if it's credit card information, obviously it needs to be. But otherwise, if it's how many cows are at the trough, probably doesn't matter.
Yes, I think it depends upon the application. People don't that, doesn't it? Somebody did ask a quick question up here. Oh, where's it gone? Is machine learning part of IoT? I would imagine the answer is it can be.
Oh yes, and it's is becoming becoming ubiquitous. Once we start combining channels, then the machine has to do a lot of the analysis, and it has to learn from it. Otherwise, can't handle big data sets.
What is the best communication protocol for IoT? Is that the old the chestnut of UDP and?
Yeah, I would have said secure UDP, because usually you want to keep the data overheads low. But the more so as time goes by, even though our networks are much more capable, we're still trying to keep those packets small.
I mentioned Zigbee before, and somebody's asked, what is Zigbee? Can you speak to that? Is Zigbee still a big player?
Yeah, big player on small networks, yes. You can still buy Zigbee devices, so Zigbee chips, which you'll install on a device, and they'll report over a radio network to a hub. So personal area networks.
I would have said sort of like Bluetooth, but different. Are actuators not considered IoT? I imagine they are. It just depends on the application. Is that what you
sorry,
think?
I missed that, Shane. Where's that?
Are actuators not considered IoT?
Oh, no, I would have thought they are. Yeah, yes, yeah.
Might be that we again, in trying to cover everything, we miss a lot of things along the way.
But Shane, if we if any of these colleagues joining the call want to write up in a few sentences that their examples that they've had experience with, and send them in, then that'd be really useful for everybody, and we can give it proper attention then.
Absolutely. Well, in the forum is the place for that as well. So the forum's at learn.itmasters.edu.au. And that is the place to go to have more, a more detailed discussion. Obviously, time and everybody trying to answer the same question at once is going to be a bit of an issue in this situation. Suraj has asked a couple of questions about security and AI and stuff. They'll be the sort of things that we will get more chance to answer either later or in the forum environment. And that's probably all for the questions. All the rest probably became answered as we went along. I will remind everybody yet again that next week, Sydney time, 1 hour later, not 1 hour earlier. Thanks again to whoever pointed that out. I think that might have been Ray again, in fact. It was indeed Ray. And we look forward to seeing you. Next week is about the business of IoT as much as anything else. It's about how to create projects, how to put them together to a certain extent, what drives them, what drives demand, why do them in the first place, and I think, we will discover that a lot of different things end up, people build stuff and they just want to put them out to market, build a better toaster and everybody will come. Well, that's not always the case, unfortunately. So in closing, I'd like to say big thank you, Jeffrey, for coming along, and lovely to see you in the flesh and your contributions tonight. Thanks to everybody. Say thanks to Lil for keeping things under control and putting messages in. I see there's 32 new messages in the stream already as I think people sign out. Have a great week. We look forward to seeing you next week, and take care as always. Good night.
Good night. Thank you.